I'm going to explain about problem number one. Step one, start with a set called A. It contains all whole numbers from n down to 1. For example, if n equal 14, then A equal something like this. Step two, take the first element of A, which is n. This will be your numerator. Now divide this numerator by a given denominator m. Let's say m equal 5 for 14 over 5. The remainder is for label this remainder as R1. Step 3. Create another set B with the same number of slots as elements in the A. Place R1 in the first slot of B. Step 4. Now take the next number in A, which is n minus 1. Use the same denominator m. For example, with 13 over 5, the remainder is 3. Place R2 equal 3 in the next slot in B. Continue this process for all elements in A. Step 5. Once B is filled, sum all its elements. That total is your answer T. Example, if n equal 14 and m equal 5, the process fills B as something like this. The total sum T equals the sum of all these numbers.
Let me walk through the problem pairwise sum and divide. Step 1, start by defining the size of the error. And for example, n equals 6. Step 2, create an array A with n elements, such as A equal 1, 3, 4, 2, 5, 8. Step 3, identify all unique index pair from A. For example, this could be 1, 3, 1, 4 based on position. Step 4, ensure all unique combination of a index are considered without a repetition. Step 5, set the sum to 0 as a start point. Step 6, for each pair, divide the first number by the second, ensuring both numbers are non-zero to avoid division errors. Step 7, ensure both numbers are non-zero integral for value division. Step 8, round the division result down the nearest whole number and add in the sum. Step 9, repeat the process for every pair, editing each result the sum. The final your answer. For example, with A equal 5, 3, 4, 2, 5, 8. Following those steps given a sum of 5.
I will explain problem number 3. Involving powers, sums and finding the last two digits of the result. We are calculating the sum of number 1 to the power n, 2 to the power n, k to the power n, and only care about the last two digits of this sum. First of all, we compute 1 to the power n, 2 to the power n, k to the power n. After take each result modular under like this. Add up the remainders. For example, 1 plus 8 plus 27 plus 64 plus 25 equal 125. Finally, we calculate 125 module 100 equal 25. Therefore, final answer is 25. To summarize, break the problem into calculating powers, apply modular, summing up and taking the final modular.
Let's me talking about problem for scale product. Step 1, generate the sequence. We start with a list of numbers. The first number is 0 and the second number is 3. After that, each number is the sum of the two before it, but we keep the result small using a trick called modem. Let's see an example. C equal 5, M equal 7. Our list is 0, 5, 5, 3, 1, 4, 5. Step 2, from the vectors, next we split the list into group of 2. These are called vectors. For example, the first pair is 5, 5. The second pair is 3, 1. The third pair is 4, 5. Step 3, multiply the pairs. Now we multiply the pairs together. This is called the scalar product. Here the formula. Step 4, count unique result. Finally, we find out how many answers are different. In our example, these results are 6 and 3. Finally, answer M equal 3. Thank you.
I will be talking about problem 5. We were given two numbers like k and n. We need to find the sum of series. The series has k terms. Each terms of formed by multiplying the position number by n. Let's solve it step by step. One. Series pattern. First term 1 multiplied by n, second term 2 multiplied by n, third term 3 multiplied by n, and so on until k terms. Let's work through the example cases like example 1, k equal 5 and n equal 3. Write out all the terms this position and sum all terms and equal 225. Example 2, k equal 4 and n equal 2. Write all the terms and get sum all the terms equal 30. Mathematical solution, we can solve this using the following steps: 4, 5, 6, 7, 8, 9, 11, and final answer is 225.
Problem 6. Fun with series. A series is an ordered list of numbers created by a relationship between terms. There are some common types. For an arithmetic series, the difference between consecutive terms is constant. To solve problems, follow these steps. Identify the first term A, the common difference D, and the number of term n. Use this formula, whereas Sn is the sum of the first n terms. For example, in the series 20, 25, 30, 35, with A 20, D 5, and N 5, the sum of the first 5 terms is calculated as 150.
Problem number 7. Circular summation. In this question, we have to imagine a circle of children, each starting with the specific number. The easiest way to tackle this problem is through an example where n, the number of students, is 3 and m, the number of rounds, is 4. Since there are 3 children, each round can be started with the ith child. 1, 2, and 1 are the numbers the students will have initially. It is shown here. According to the problem statement, in round 1, the ith child will sum his number with the sum of the 2 neighbors. The number of all other students will remain the same. It will give A1 is equal to 1 plus 2 plus 1. That will be equal to 4. And it is shown in the first column of the table, circled in red. A2 is also equal to 4 and A3 will also be 4. This will continue up to 4 rounds. And at the end of the 4 rounds, the numbers the students will have at the end of the game are shown in green color at the last column of the table. Well, if the numbers are very large, we can use modulo 10 to the power 9 plus 7 to deal with this problem easily. Well, this sums up the explanation of problem number 7.
Today, I will explain a problem about counting solutions to system of linear congruence modular a prime P. The system is A times X equal B mod P, where A is a matrix and X is a vector of variables and B is a vector of constants. Our goal is to find how many configurations of A and B produce exactly a solution. Under constraints like fixed zeros in A, the solution count depends on the rank of A modulo P. If consistent, it is P into the power n minus R. To get S, we compute the required rank and count valid matrix A of that rank, ensuring consistency with B. Efficiency modular arithmetic and Gaussian elimination help handle large computations, and the final result is sum modulo 10 into the power 9 plus 7. It is a clever mix of algebra and optimization. Thank you.
I will be talking about problem 9. We can assume the input will always be a list of integers. We have demonstrated the exclusive OR function here. The generalized way to do this problem is as follows. Consider a subset S of elements from set A where S contains all elements in the range P to R, where P, R, and K are values from the query which are given to us. For each unordered pair X, Y, we need to calculate Z, where Z is a result when X and Y are fed into the exclusive OR function. We need to keep track of the sum like this. Finally, we need to take the modulo with 10 to the power 9 plus 7 and sum. That will give us the result. Now let's go through an example. Here we have our query. Here we have the input set. Step 1 is to extract the subset S. Step 2 is to use the exclusive OR function on all pairs in S. For example, for this pair, we need to follow these steps to arrive at the final sum, which is 3. Finally, we need to sum the results. The results are 0, 3, and 2. We need to add them up and we will end up with 5. Now we need to calculate sum modulo 10 to the power 9 plus 7. The result will give us 5. That is how you solve the problem.
Let me explain rational sum. First, we define two components, Qn, a product of terms based on number like Pn, a simple polynomial like. Second one, for each number n, we calculate Pn over Qn, a ratio. For example, for n is equal 1, we calculate Q1 is equal 24 and P1 is equal 9, giving 0.375. Similarly, for n is equal 2, we get 0.233, and for n is equal 3.1583. Third one, add these ratios for all n values to get an approximate total. In this case, adding the first 3 gives